Hello dear students. So now we will see example 2.7, which is a problem of method of characteristics. Solve the equation ux plus 3y to the power 2 by 3 uy equal to 2 subject to the initial condition u of x1 equal to 1 plus x. So here the coefficients are functions of x and y. Also the initial condition is given like this: when y equal to 1, we have x takes any value. When y equal to 1, u is the curve 1 plus x. This is the initial condition. So as usual, we will write the characteristic equation and initial condition. So we have xt equal to 1, yt equal to 3y to the power 2 by 3 and ut equal to 2. Now we will write the initial condition: x of 0s is equal to s, y of 0s is equal to 1 and u of 0s is equal to 1 plus s. Now we will just see what is the Jacobian in this case. So Jacobian is determinant AB dx naught by ds dy naught by ds. So here A is 1, so we will get 1. B is 3y to the power 2 by 3. We have to evaluate B at the initial curve. So initial value is y equal to 1. So when you put y equal to 1, we will get 3. Now dx naught by ds, so x naught is s, so dx naught by ds is 1. Y naught is 1, so dy naught by ds is 0. So we can see here the determinant is minus 3, which is never 0. Hence we expect a unique solution in the neighborhood of the initial curve. Now we will find the characteristic curves. For that we will solve the characteristic equation. So the first equation is xt equal to 1. So that is dx by dt equal to 1. So when we integrate, we will get x equal to t plus f1 of s. Now apply the initial condition: x at 0s is equal to s. So when t equal to 0, you will get f1 of s is equal to s. So we are getting x is equal to s plus t. Now the second characteristic, the other equation is yt equal to 3y to the power 2 by 3. So when you integrate, when you separate this, you will get y raised to minus 2 by 3 dy equal to 3 dt. When you integrate this, we will get 3y to the power 1 by 3 equal to 3t plus f2 of s. Now when we apply the initial condition, we have y at 0s is equal to 1. So when t equal to 0, when you put t equal to 0, we have y is 1. So we'll get 3 equal to f2 of s. So when you substitute here, you divide throughout by 3. So you will get y equal to t plus 1 whole cube. Now the third one is ut equal to 2. So you can directly integrate u equal to 2t plus f3 of s. Initial is u at 0s is equal to 1 plus s. So t equal to 0, f3 of s become 1 plus s. So u is 2t plus 1 plus s. So we thought that we are getting a unique solution. We did not encounter any problem here. But now let us see what is the projection of these characteristic curves and the initial curve. Okay. So we have y is equal to, here we have y is equal to t plus 1 whole cube and t is x minus s. So we have y is equal to x minus s plus 1 whole cube. Now to find the projection, we have to fix x. So for each fixed x, this is the equation of a characteristic. We are getting some x plus c whole cube formula. Okay. Now the projection of the initial curve gamma. Now what is the initial curve gamma? We see that initial curve is x equal to s, y equal to 1. So x can take any value, y takes the value only 1. So it is a line y equal to 1. So we have y equal to 1. This is the projection of the initial curve gamma. This is the projection of initial curve. And what is the projection of characteristic? Projection of characteristics are curves of the form x plus c whole cube. Because s is fixed, so this is of the form y equal to x plus c whole cube. So just like y equal to x cube, or it is not x cube because here some constant is there, so it does not passes through origin. So we have curves of this form. Okay, this form curves have. Now we see that the curves intersect the curve y equal to 1 only once. Okay, the characteristic curves meets the initial curve gamma only at 1 point. But there is a problem. In this question, we see that the coefficients, they are not smooth. Here the coefficient is 1, no problem, but here the coefficient is y to the power 2 by 3. That will create a problem because this equation does not satisfy the Lipschitz condition. You have studied this in ODE also, we have done this problem. The reason is that this ODE does not have a unique solution. They have more than one solution. Because if you take yt equal to 3y to the power 2 by 3, y equal to 0 is also a solution for this equation. We have done the same problem in ODE when we studied about the Lipschitz condition. So this coefficients are not smooth. That is the problem here. Okay, so since the coefficients are not smooth, coefficients of the PDE are not smooth, the ODE need not have a unique solution. There may be many solutions for the ODE. In particular, this equation has a solution y equal to 0 is also a solution. That is, x-axis is also a characteristic curve. Now see the figure. So we got one. Now x-axis is also a characteristic curve. Now these are also characteristic curve. So characteristic curves are again intersecting another characteristic curves, which will create problem. So the characteristic curves are intersecting this new characteristic curve, that is y equal to 0, that is the x-axis. So we expect there is some irregularities near the x-axis. Okay. Now when we invert the transformation, we see that we have x equal to t plus s, y equal to t plus 1 whole cube. So since the Jacobian is non-zero, there is no problem in inverting the transformation. So we can invert the transformation from ts to xy. So we will get that u equal to 2t plus s plus 1. So which is, we substitute for t and s. So we will get like this. If you simplify it, we are getting u equal to x plus y to the power 1 by 3. Again 1 by 3 is there. Okay. And this is singular on the x-axis. So we are able to, there is no problem if we neglect the x-axis. In the neighborhood of x-axis there is problem, otherwise there is no problem and it will have a unique solution. Now we will see another problem, example 2.8. Solve the equation y plus u into ux plus yuy equal to x minus y subject to the initial condition u at x1 equal to 1 plus x. Now again we will write the characteristic curves. Characteristic equation are xt equal to y plus u, yt equal to y, ut equal to x minus y. Initial conditions are x at 0s is equal to s, y at 0s is equal to 1, u at 0s is equal to 1 plus s. Now we will see the Jacobian. So Jacobian is here a is y plus u. We have to find y plus u on the initial curve. So on the initial curve y is 1, u is 1 plus s. So this become 1 plus s, so 2 plus s. B is y is 1, so 1. Dx naught by ds is 1, dy naught by ds is 0. So when you do this, we are getting determinant is minus 1, non-zero quantity, and hence we can expect a unique solution in the neighborhood of the initial curve. Now we will solve this. So here we have xt is equal to y plus u, yt is y. So you can see these are coupled equation. We cannot directly integrate it. We have to do it simultaneously. Okay, because here y is coming, here also y is there. So when you differentiate it once again, so we can use some ideas here. If you do xt plus ut, what you are getting, xt plus ut will give you, y will get cancelled, it will give you x plus u. Okay, so x plus u, this is derivative of x plus u, so direct integration is possible. That is derivative d by derivative of x plus u by x plus u equal to dt. When you integrate, you get log x plus u equal to t plus some constant which is a function of s. We will take log also, so log f3 of s. So you will get x plus y equal to f3 of s e raised to t. Now we have the initial condition x at 0s is equal to s and u at 0s is equal to 1 plus s. So when you give the initial condition, you will get f3 of s is equal to 2s plus 1. So we are getting x plus u equal to 2s plus 1 into e raised to t. Now we have the next equation is ODE is xt equal to y plus u. Now again we cannot directly integrate this because here y, u, all terms are coming. So we can differentiate it once again. So we'll get xt equal to yt plus ut. And we have yt is y and ut is x minus y. You substitute it, you are getting xt equal to x. Now we got a second order ODE in x alone, which can be solved very easily. Because its auxiliary is m square minus 1. So we have m equal to plus or minus 1. So x is f1 of s e raised to t plus f2 of s e raised to minus t. Now we apply the initial condition x at 0s is equal to s, which implies s equal to f1 of s plus f2 of s. So we have only this condition f1 plus f2 equal to s. So we can take any arbitrary value. Suppose let f1 is 1 plus s, then f2 of s must be minus 1, because when you add it you are getting as s. So we get x is equal to 1 plus s e raised to t minus e raised to minus t. Now to invert the transformation, now we put 2 in equation 1, so you will get the value of u also. We will get u equal to s e raised to t plus e raised to minus t. Now we have to get y also. We got x and u. Now to get y, we have ut equal to x minus y. And we substitute x minus y here. So we have y is equal to 1 plus s e raised to t minus e raised to minus t minus s e raised to t plus e raised to minus t. Simplify this, so you will get y equal to e raised to t. Now we can invert the transformation. So we have u is s e raised to t plus e raised to minus t. Now we can substitute the value here. So s e raised to t minus this we can write it in this form. E raised to minus t can be written as minus e raised to t plus 2 e raised to minus t. So you will get u equal to x minus y plus 2 by y. So this we are able to invert the transformation and we got the integral surface. Now here also we got a local solution which is well defined near the initial curve. Near the initial curve it is defined because initial curve does not has the value y equal to 0. This solution is not global because it has a problem near x-axis. X-axis means y equal to 0. At y equal to 0 there is a problem. Hence the solution is not global, but it is a local solution. We have a unique solution in the neighborhood of the initial curve. There is problem near the x-axis. Okay, so in this way we have discussed 2 problems here. Okay.